Welcome to lecture 8. So this is our last aspect on the fundamentals of the colloids. So today we are going to discuss that what or how to characterize the colloidal particles based on the optical properties. So that means first we will focus that how to visualize the colloidal particles. So of course, by definition, if we think about that, we take suspension phase as a fluid, that means either is liquid or air or gas. Then we can think about we have colloidal particles means some solid suspended phase. So, and by definition, the size range of the solid suspended phase, as I told you, that it ranges from few nanometers to few microns, okay, or maybe few hundred microns at the most. So obviously, when we talk about nanometer and micrometer, so that means the particles are smaller than that would be visible by the human naked eye. So obviously the answer is how to visualize. So we can only visualize by microscopy. So the question once again, that what kind of microscopy we can use to visualize the colloidal particles. So we first start with the optical microscopy. So I hope that every one of you have seen a simple light microscope in your high school basic biology laboratory. Okay, so the light microscope is a kind of an optical microscope. So before we proceed, there are two fundamental questions, there are two fundamental aspects that we have to take care of. So that is, there are two terms. A is, there is a term called resolution, and B, there is a term called magnification. Okay, so that means using these two words, we are going to assess that how small a particle can be visualized by optical microscopy. Okay, so basically these two words define that how small can a particle be for visualization using a microscopy. So it could be an optical microscope or some other microscopic technique. But let's first try to have a definition of this resolution and then magnification. So the term resolution actually stands for, say, I am just drawing two spots over here. Okay, you can see that. So the distance between these two spots, I call it delta. All right. So in microscopy has a limit. So that means you can visualize a minimum distance, or it's better to put it this way, there exists a minimum distance delta for which these two dots can be distinctly visible or distinctly separable from one another. Okay. So in other words, this resolution defines how well you can distinguish between 2 points on an image. Compared to resolution, the magnification is a much trivial concept, because we can magnify an image by any extent. So it is possible, it is not a very big deal. But the single most important factor is the resolution. So without the resolution, the magnification does not have any meaning, because you can magnify million times, okay, but the question is, can you extract the important information that you require or any useful information from that image? Answer is no or yes, provided you have the adequate resolution. So that means the distance delta, it is defined as a resolution between the two. So 2 points. So the delta can be defined by mathematical equation. So the mathematical equation is lambda divided by 2n sine alpha. So now I'm going to define what are these terms. So first take a look at lambda. So lambda is the wavelength of the light or any other electromagnetic radiation we can use to for microscopy. And then the rest of the values we can define it this way. The L stands for the refractive index of the medium where we are actually doing this microscopy. So that means it is the medium between the objective lens of the microscope and the sample. And alpha is called the angular aperture. So this is how the alpha is defined. Suppose this is the tip of my objective lens right here, okay? And this is the sample, means the field of view. So we can make an angle just by joining these 3 points. So this is basically a triangle. So half of this angle is called the alpha, angular aperture. Okay. So now this term n sine alpha, this is also called the numerical aperture in microscopy. All right. So now let's come to the point here. Resolution delta. So before we begin, let's first ask a question that what is the delta for human eye? So that means what is the least distance we can recognize with our normal naked eye between the 2 points. Okay, the answer is delta for human eye is on an average it is about point, or rather I would say it is 2 millimeter. Okay, or in other words, this is 2000 micron. So therefore, we need microscope to see smaller objects. So what kind of microscope we would start with? So let's start with our first microscopic technique, that is, we start with this optical microscopy. So in optical microscope, it is just the lights that helps you to see the objects. So remember, using this optical microscopy, we don't necessarily increase the magnification, okay, or we don't magnify the objects. We also take care that enough resolution is there, that means delta. Now if we look at here, delta is lambda divided by 2n sine alpha. So then the question is that in optical microscopy, how these parameters actually behave. So for light, if we talk about optical microscopy usually means using visible light as lambda. Okay. So what is the range of lambda for visible light? So lambda for visible light, we know this is in the range of 400 nanometer to 750 nanometer, roughly. All right. So the thing is how to increase delta resolution using optical microscopy. So we can't do much about this lambda because our visible lines is already fixed. So what we can play with is the n sign line with n sign alpha values. Okay. So one thing is for sure with alpha. So what alpha means, if the alpha is smaller, uh, or in other words, the entire thing in the denominator is smaller, that means lambda has a high value. But we want the other way around. That means we want to reduce the lambda, delta value as much small as possible. So therefore, we would go for a high alpha value. So that means if you reconsider this image, so having a high lambda means high alpha means your object or the field of view of the object should be as close possible to the your objective lens. All right, so we have a wider angle, so that means we have a wider alpha. So this way we can adjust a little bit, but beyond the limit we cannot improve the alpha because there is a question that how much you can focus also, and not only that, if you reduce your alpha, if you increase your alpha too much, you would also lose the depth of field. So we can write that higher alpha means reduced depth of field. So we call this thing as DOF, depth of field. So depth of field means whenever we are talking about this vertical distance, so if we call this distance as Z direction, so how much of the field is in focus in the Z direction, so that is called depth of field. So if you increase the alpha too much, this depth of field gets reduced. Alright. But there is still one way to improve the numerical aperture still, because here there is the term n. N is a refractive index. So now we can definitely try the microscopy in a medium with an increased refractive index. So can you think about what are the mediums that are having an increased refractive index? Okay, so for example, I can now take a name that is in normal optical microscopy, it is done in air. Okay, but if we think about oil, the refractive index of oil is greater than the refractive index of air. So that means if we take our normal microscope and if we replace the air between the objective lens and the sample with oil, it will give you better resolution theoretically. And I'm not kidding, it is actually done. And so under optical microscopy, we have a special kind of microscopy which we call an oil microscope. So an oil microscope it is also known as oil immersion microscope. It is a part of optical microscopy where we are having an improved resolution due to n sine alpha. So n sine alpha in air, okay, which is close to the value of something like 1 in air, okay, but the same thing in oil, it can be 1.5. So therefore, we can easily improve the resolution of optical microscopy when we have an oil immersion microscope. All right. So now the question is, with all the best possible efforts, what is the least value of delta we can achieve through optical microscopy? Even you can take the oil immersion microscope. So the answer is the delta least, okay, in kind of in any sorts of optical microscopy. Okay. So this goes to a value of 0.2 micron or 200 nanometer. Okay. So now you see, if you can resolve a distance of 0.2 micron, but the problem is our human eye resolution, so we can write that delta least human vision is about 2 millimeter. Okay, so that means it is 2000 micron. So therefore, resolving 0.2 micron is not enough, so you have to magnify. Okay, so now here we have to take the help of magnification, so we have to have powerful objective lenses to magnify such small resolution to be captured, to be distinct, or to be recorded by human eye, because human eye's resolution limit is only 2 millimeter. So you have to magnify a distance of 200 nanometer to 2000 micron. So how many fold would you have to magnify? So if you can do your maths correctly, so 2 millimeter means 2000 micron. So that means it is 10 to the power 4x. Okay, so 10,000x or 10,000 times you have to magnify at least for a human to be able to distinguish between the 2 points. Okay, so the bottom line is with using such factors for resolution, using optical microscopy, or better oil immersion microscope, we can achieve a resolution, or we can see particles up to 200 nanometer. All right, but the question is, the colloidal particles may be smaller than 200 nanometer that we have seen earlier. So how to visualize those particles? So again, the answer is hidden, lying here. So you see that using visible light, we cannot do anything beyond 400 to 700 nanometer of visible length, visible wavelength. So now we have to change the lambda. So we have to take a wavelength smaller than the visible wavelength. Then it is possible we can reduce the delta further. So the question is how we can reduce the lambda. So what kind of electromagnetic radiation we can think about. All right. So now we move on to discussing very briefly about electron microscopy, where we would use the electrons as a primary source of this lambda, okay, for microscopy. So let's clean the board and move on to some very basics of electron microscopy. So the basic idea behind electron microscopy is to take the advantage of the smaller lambda. So if we remember that for optical microscopy, the lambda range was, if we talk about in angstrom, so it was from like around 4,000 angstrom to like 7,500 angstrom, if you remember. But if we think that we can have a wave of electron in the form of a beam, focused electron beam, the wavelength of the electron can be in the order of several angstroms only. So, and this wavelength can be tuned. So easily we can have few tens to few hundred angstrom of wavelength of the electron beam. So with that, the electron microscope that was first developed, it was known as transmission electron microscope, or the technique is called the transmission electron microscopy, and is famously abbreviated as TEM. So with everything well tuned in a TEM, the best possible resolution can be achieved is around 0.2 nanometer. Okay. Now the thing is, remember that although electrons in general we understand these are particles, but after the work of Louis de Broglie, we have seen that the electron have wave-like properties. So the wavelength of the electron can be expressed by this equation. All right. So here P is at the bottom, means at the denominator. The larger the momentum of the electron, the smaller is the wavelength. So if we have some electrons accelerating between two across two high voltages, the higher the voltage, the higher the speed of the electrons, the higher the momentum and lower the wavelength, lambda. So with that, the least wavelength, the least resolution we can get is 0.2 nanometer. But remember, for TEM, this limit is not due to the limitation coming from the lambda. Okay, we could have gone further, down, but this limitation or this limit is bound by two factors. That is, the one is the stabilization of high tension electron beam. Okay, that is the number one, and number two, that is another factor that is called the lens aberration. Okay, so you have to have proper lenses. So remember, we do not use optical lenses that we use for the typical light microscopy or oil immersion microscopy. So in transmission electron microscopy, the lenses that we use, those are basically some electromagnetic coils. Okay, so basically electromagnets. So there is a possibility that there is a high degree of aberration of electron beams associated with it. So due to the stability of the electron beam and the limitation of the aberration experienced by the lens, the resolution is limited up to this point. But with TEM, we can easily observe any particle from the size range. So particle size range is from 1 nanometer up to 5 micron. Easily we can distinguish, we can characterize. So and it is not possible to visualize atoms in TEM because because of the Heisenberg's uncertainty principle, atoms always look blurry. Okay, because we cannot visualize the electron cloud in that manner. Anyway, so if the delta is 0.2 nanometer and delta for human eye, once again I'm writing, is 2 millimeter. If it is 2 millimeter, then you can do the math that what kind of magnification you require to visualize a distance separated by 0.2 nanometer in electron microscopy to be observed by a human, okay, which is with a 2 millimeter resolution limit. Okay, so you may need to do the math. So so that you can see the magnification is actually going in millions. Okay, so you see like several hundred thousands or even a million times magnification is required. So in transmission electron microscopy, those electromagnets actually make such magnifications. But one disadvantage of the TEM is that there is no DOF, that means there is no depth of field available. It is because this is the science of transmission electron microscopy is designed in such a manner that it's almost like viewing a projection image, not the actual image. So therefore, it doesn't have any DOF. It just gives you an idea that how big or small the particles are. Okay, but If you want to visualize particles with better DOF, then there is another technique which is developed much later. So this transmission electron microscopy was developed in 1930s. Remember, even before the Second World War. So and then much later, another technique it is known as scanning electron microscopy, or in other words, in abbreviation, it is known as SEM. So it is developed, but its resolution limit is around 5 nanometers. So you lose some of the resolution here, but the advantage is that it has a great depth of field. That means you can almost visualize a three-dimensional feature of any particles. So it is very useful technique for observing colloidal particles. The basic principle of the transmission electron microscopy and scanning electron microscopy are the same, because you need to have an electron gun to generate a beam of electrons, and that beam of electrons through some electromagnetic lenses has to be focused on samples. But the only difference here is that how you observe the sample. Okay, so for TEM and SEM there is a difference. So I will, at the very end of this course, I will come to the basic principle of the electrons that we used to see or characterize these colloidal particles. That will come to that later. But I can tell you one very basic thing is the image that is generated in SEM is actually from some electrons that are coming back from the samples to the detector. But for SEM, in TEM, we actually observe the beam directly after it has interacted with the sample. But here we see some electrons, and those electrons are called secondary electrons that are mainly generated after this electron beam interacts with the samples. So anyway, we will come to those things later. So overall, this scanning electron microscopy gives us a very good way to understand the particle morphology of or the size, or not only size, shape, and the surface roughness, etc. Through this. But there is one little disadvantage of the electron microscopy is that you cannot characterize a colloidal salt as is, because they are colloidal salt means some colloidal particles in air or in liquid medium, right? So you cannot just take this thing and study this SEM and TEM microscopy. So you have to have you have to prepare the sample separately, where you have to take those suspended medium, that means the solid particles, out of the system, and you make the samples in a special manner. So the time that you are visualizing these things using electron microscopy, those are not in a colloidal medium anymore. So they behave just as solid phase particles. So therefore, this electron microscopy technique is not good to capture how colloidal particles behaves as is when they are in a suspension medium. For that, we need another kind of microscopy, and that microscopic technique is called ultramicroscopy. As I remember, I mentioned it during the discussion of particle electrophoresis, that the movement of those particles during those electrophoresis is observed by microscope. That's why it's called microscopic electrophoresis. So next, I'm going to discuss the working principle of that ultra microscopy. So that ultra microscope could be useful to visualize suspended particles as is in the colloidal medium. Okay, so let's clean the board and discuss that. So now we will talk about ultra microscopy. So this is the technique by which we can characterize the colloidal suspension as is within the dispersion medium. So this technique is developed by Zygmundi. Okay. And so this the principle, the basic principle of this ultramicroscopy is dependent on an effect. It is called a Tyndall effect, and this is basically a scattering phenomenon. So we can also call it it is the process of a Tyndall scattering. So what is Tyndall scattering, that we will come to the point in the next lecture. But the necessary condition for this Tyndall scattering to happen, that there should be a significant difference of refractive index between the solid particle and the dispersion medium. So that is the most important criteria has to be there. Then only the Tyndall effect and scattering would take place. And not only that, what kind of particles would undergo this Tyndall scattering? So basically, this scattering effect is observed where the particle size dimension falls in the visible range. Okay, so that means we can just write like that, that it should be, the particle size range should be somewhat between 400 nanometer to 800 nanometer. Okay, or at the most 300 to 350 nanometer to 800 nanometer. So basically this is the visible size range of the particles. So that means here if we talk about the resolution, once again delta, so you see these delta, the range of delta is almost like the optical microscopy. That means within the, that means where whatever the resolution is limited by the wavelength of visible light, the same kind is applied here, because this ultramicroscopy is done by some visible light. So the question is then how to observe these particles. Okay. So therefore, in order to explain that, I need to clean the board and to draw. So now let's discuss the basic working principle of ultramicroscopy. So as I told you before, that it is based on the Tyndall scattering mostly, and in some cases it's also based on a special type of scattering called NIT scattering, which I will going to talk about in the next lecture. So in the basic working principle, we can assume that the sample is in the form of colloidal suspension, where the light source and the optical detector is kept at an angle 90 degree with respect to each other. So once the diffracted light source is focused on the sample chamber, if it is not scattered, so the light goes as it is. So this is the direction of the incident light. That means also the unscattered light. So this is the path of the unscattered light. But when the light scattering happens, the probability of finding the scattered light is the maximum at an angle 90 degree with respect to the incident direction of the diffracted light. So once the microscope is kept at an angle 90 degree with the incident beam, whatever the scattered signals are coming from the Tyndall scattering or Tyndall effect from this solution, that is going to captured by the detector of the microscope. And as a result, what happens? So in absence of any scattering, we generally see a dark background. Okay, so we can call this is a dark background in absence of scattering. And then whenever the scattering happens, we will see a signal as a bright spot against the dark background, so something like here. So this bright spot would signify the presence of the particle itself, and also the spot size would tell us about the size of the particles in the colloidal dispersion. So since this is observed with respect to against a dark background, so this ultramicroscopy developed by Zsigmondy is also known as the dark field microscopy. Okay, so what is the application of such ultramicroscopy? So as I have already mentioned a few times earlier, that is one of the major application is to track the Brownian motion of certain particles, and then its major application is in the particle electrophoresis. So the earlier electrophoretic particle electrophoresis machine used to have exactly the ultramicroscope, and now these days basically the same technique, but it has been evolved in a little bit more advanced way, so that I will also talk about little bit in the next lecture. And also the size analysis of any colloidal particle suspended in a liquid or air. So at the beginning I told you that the only way we can distinguish a pure solution versus a colloidal suspension, that the colloidal suspension mostly would undergo the Tyndall effect. That means that should be visible by an ultra microscope. And while doing the size analysis, we can get information about the relative diameters, and also another term that is called the dispersity. So we can get an idea about the dispersity of the particles. So this is probably a new term I'm introducing here today. So I'm going to describe this term dispersity. What does it mean? So I'm going to clean the board and I'm going to discuss it in the next. But before we go, just a little bit of correction here I would like to make, that through the ultramicroscopy, what are the particle size range we can typically record. So the size range of the particles that respond to this ultramicroscopy is between 40 nanometer to 900 nanometer. So earlier I told you that from between 400 to 800 nanometer, but there is a correction to that. So because this is mostly in the range of the visible light, but it can go slightly below it. So almost like one order magnitude below. So basically from 40 nanometer to 900 nanometer. So anyway, so our next topic of discussion is dispersity. So let's clean the board and describe it here. So whenever we study the particle size by microscopy, we actually develop one of these two types of graphs. What are those? So here we plot the particle diameters in the x-axis, and the number of particles or the percentage of particles having that particular diameter we plot in the y-axis. So usually we get a variety of diameters. That means suppose we are thinking about a particle, expecting that the particle would have a diameter around say 300 nanometers, but we can get as low as 100 nanometer and as high as 600 nanometer. So therefore, we can have a distribution of particles according to their diameters. So this kind of distribution is also called a histogram or a size histogram plot. So like this, it can go. So that means very small diameters will have a very small percentage expected as a natural distribution, and very high the particles with very high diameter would be having smaller in number, and in the medium we have, in the middle we have the maximum number of particles. So from this we actually generate an average diameter, as opposed to sometimes what happens that or it should be the ideal one, that when all your 100 means all the particles, the 100% of the particles having a particular distinct diameter. So suppose this number is say x, and we have all the particles over here. So I have just drawn a line there. So this can be 100%. So whenever this situation arrives, so we call the particles are monodisperse. So that means all the particles are of same size, so there is no particle size distribution. And whenever we get a situation like this, we call the particle as polydisperse. So that means different particles have different sizes, and we have a distribution of sizes of different particles. So overall this thing is called dispersity. So dispersity of can be of two types, either it is monodisperse or it could be polydisperse. So anyway, and so where from polydispersity arises? So one of the reasons is the polydispersity, that we actually can have different sizes of particles like this, but as opposed to here in monodisperse, we have all the particles are of same sizes. So this is the ideal situation. Okay. But this is the non-ideal, so different particles will have different sizes, we have a distribution of sizes. But also, think about this one, so even if we have originally monodispersed particle, but depending on their degree of aggregation, we can still have a polydispersity appearing in the graph. So that means what I'm trying to say, suppose there is one particle here and the same size of particles, they may aggregate or agglomerate like that. So, and sometimes the aggregation is heavier, something like that. Okay, so although each of the particles are almost same size, but due to their different degree of association with each another, so with the different degrees of aggregation or agglomeration, we still have a polydispersity appearing. So it actually depends on the nature of the colloids and their surface properties. Alright, so this much was about the characterization of the colloidal particles based on their optical properties. So in the next lecture, we are going to talk about the scattering of light by colloidal particles, and this is one of the very important aspects of the characterization of colloidal particles. So we'll see you in the next lecture. So till then, goodbye.